In this video, we're going to look at the process of anti-differentiation. Again, we hear the prefix anti. It just means the opposite of the derivative. So we call that the integral. This word differential equation is just an equation that has a derivative in it. So it could be a derivative. It could be in terms of a derivative, but that's what a differential equation is. An indefinite integral is the set of all of the antiderivatives. And so remember we discussed with slope fields, we have an infinite amount of them. So we're going to discuss how we write all of them. And that's because those constants have derivatives that are zero. So the word indefinite integral and antiderivative are exactly the same. And the definition, basically, once you anti-differentiate, if you can take the derivative and get back to the function they gave you, then it's the antiderivative or the integral. Again, it's the inverse of differentiation. So again, because there's an infinite amount of integrals, and that's because those derivatives of constants are zero, we do have to put a plus c at the end when we are finding indefinite integrals. Again, that's because we don't know what constant we started with. So we have two things. One is called a general solution, and one is called a particular solution. A solution to a differential equation is just the original. And remember, in a general solution, general just means kind of like, all of them, we have to have that plus c. They all have to be in this form of plus c. Particular means I want one of them, so one particular. So we're going to actually find the value of c. And to do that, we're given an initial condition that's in the form of some ordered pair. So again, it's indefinite is the set of all of them. So this is kind of what it looks like. This guy is my integral symbol. We call this function the integrand. This tells me what variable is in the problem. Again, that's very important because we are going to be changing that. And sometimes we're going to have two variables in the problem. And then this guy's called your constant of integration. So here's our formulas. Again, these are just the inverse of the differentiation formulas. So it's literally backwards of differentiation. So in differentiation, constants drop. In integration, they also drop. Sometimes we can even pull them way up front just to make the problem look a little bit easier. There is no sum and difference rule. This could be a plus or a minus, and those formulas still both apply. There is no, we have to have a certain product and quotient rule for differentiation. So we have to do something special when we do that for integration. When we're taking the derivative, number one, we multiply the exponent by the coefficient. And then we subtract 1 from the exponent. In integration, we're going to do that backwards. So in integration, we're actually going to add 1 to the exponent, and then we're going to divide that coefficient by the new exponent. So we're just doing everything kind of backwards and opposite. So these formulas here, because they have special differentiation formulas, they do have special integration formulas. So you may want to pause and write these down. But when we're differentiating, we go this direction. So if I see any one of these formulas, I know I'm looking this way for its derivative. If I'm asked to integrate, I'm looking for these formulas. If I see that I'm integrating secant squared, I know the answer will just be tangent. If I'm integrating the cosine, I know the answer is just going to be the sine. If I'm integrating negative sine, I know the answer is just regular cosine. This negative can be moved. That can be treated like a constant. So I can pull that out if I need to. Okay, so again, we do have to rewrite before we integrate so that we can use that power rule, just like differentiation. So I'm going to want to bring him up, and I'm going to write him as x to the negative third with respect to x. When I integrate, again, I just do the reverse of the power rule. So first I'm going to add 1 to that exponent, and then I'm going to take this original coefficient, and I'm going to divide it by whatever I got here for my new exponent. So my new coefficient is going to be negative 1/2. And then we always have to add that plus c. Remember, I'm looking for the original, and I don't know what constant was there. Okay? The next one, I'm going to integrate really x to the power of 1/2 with respect to x. Again, I'm going to add 1 to that exponent, so now I get 3/2. And then I'm going to divide this original coefficient by 3/2. Remember, when we divide fractions, we actually flip this guy and multiply. So I'm really going to multiply by 2/3. Remember, we can check these by taking the derivative of this function and making sure we get this integrand. Okay, down here, there's really, we don't need to rewrite this guy. Remember, coefficients, though, can come out front. When it's really ugly, I think this process is worth it. If it's just this, I probably would have left the 2 in. But we know that sine and cosines are opposites, and the derivative of cosine is negative sine. Since there is no negative here, I need 1 in my answer. And then don't forget, this guy is going to drop down. Just make sure, again, we can differentiate this guy and make sure that we get this integrated. So again, we have the power rule. This is pretty straightforward. We're going to add 1 to our exponent and then divide. So here we get a coefficient of 3/5. Okay, out here we'll get x to the third. When I divide -5 by 3, I get -5/3. Lastly, the x, I'm going to add 1 to my exponent and then divide. And just don't forget, we always have that plus c at the end. We're finding whatever that original function was and we didn't know it. Sometimes with trig, we do need to rewrite. Again, there is no quotient rule or chain rule. That's both good and bad. The process of dealing with this is pretty difficult, but there's only one process to learn. So if we can, we want to rewrite this. So remember, this is the same as sine of x over cosine of x times 1 over cosine. And so I want to rewrite this into one of those derivatives that I know. So I'm looking back at these trig functions, and I'm trying to get it to look like something here on the right-hand side. And I should notice, hopefully, that this guy is the same as tangent. And hopefully I notice that this guy is the same as secant. And I know from those formulas that secant tangent is the derivative of just the secant of x. So that's my integral. Just don't forget your plus c. So now we're going to talk about how to find a particular solution. So all these last guys were called general solutions because this is the general form of every original function. Every original will be in the form of secant of x plus some number. Now we're going to find that some number. So remember, we're given 2 pieces of information here. One is the derivative, and this guy is giving us some information about the original. So I have to go back to the original first, and to do that I integrate. Don't forget, we do have to say what we're doing. And to save time, you don't have to write the whole function out. You can just say, I'm going to integrate this function. When we integrate then, again, we're going to add 1 to our exponent first. So I get x cubed, and then we're going to take that coefficient and divide by that new exponent. Out here, we're going to do the same thing. So we get x to the second. When I divide coefficient by new exponent, I get 1/2. And lastly, I'm going to have 7x plus c. And this is equivalent to the original. Just like differentiation, if this guy's labeled, we must label our answer. And I labeled it wrong. I labeled it as the derivative, and it's actually my original now that I have integrated. So this should just say, I'm actually going to write it on the right-hand side so that I have room. This is going to equal the original function. And so for a particular solution, we need to find the c. So in order to find a value, I need to know values for both x and y. And we just so happen to have that here. So we're going to plug that in. So my y value is 1. And my x value is 3. So when I cube 3, I get 27. So this is really 27 over 3. When I square 3, I get 9. So I'm going to have 9 over 2. And here, when I multiply, I'm going to have 21, and I still have plus c. And so now I'm going to solve for c. So you can see here that I've gotten c by itself. And now I need to write my particular solution. So my particular solution, again, is that one original that goes through that ordered pair. So it's going to be 1/3 x cubed plus 1/2 x squared minus 7x plus 8.5. So my general solution is the general format of every original. It's got a plus c in it. My particular solution is the one in that form that also goes through that point I had back up at the top.